Now we talked about concentration's effect on reaction rate, and we spent the last couple of days actually talking about the role concentration plays in a first order, a second order, zero order reaction. We graphed it, we came up with those integrated rate laws, but it's now time to move on to temperature's effect. How does temperature affect? Well, we know temperature increases, the rate increases, and that's an interesting observation, but this is AP chemistry, so we're going to talk about why that is the case. Observe this reaction. Now you've got H2 bonded to Cl2, and they need to come in contact with one another to create 2 molecules of HCl. Now how is that going to happen? Well, in fact, you might not think it matters, but the orientation of how these 2 molecules come in contact with one another makes a big deal. Now if they come in this way, head to head, where the H2 hits the Cl2 head to head, in fact, this reaction is not going to happen. The orientation is not correct in order for this to make the 2 molecules of HCl. So what's going to happen here is that you'll have H bonded to H actually line up broadside, not necessarily head to head like you got right here, but broadside, so that the H2 and the Cl2 can lie next to each other on top of one another. And I'm going to draw in red here these partial bonds beginning to form. This is what is known as an activated complex. This is a square-looking molecule that has partially broken H bonds and Cl bonds and partially forming HCl bonds. Now you might be asking yourself, what's temperature's role in this? Well, if molecules are allowed to move around at their normal temperature, every once in a while you'll get a couple of molecules doing this over here. And that's good. I mean, if hydrogen wants to break its bonds and form bonds with chlorine, then this is the ideal situation. Now what you can do is, as you increase the temperature, this happens more frequently. You get more molecular movement, more bumping into each other, and more activated complexes forming by random molecular motion. Some people think that temperature increases the likelihood of just one molecule crashing in with just the right amount of energy to make the reaction happen, but it actually is increasing the average, or the speed and energy of all of the molecules, and what you're getting is a more likelihood of an activated complex forming. Now let's take a look at the same chemical reaction that we looked at on the last slide, but also factor in something called the potential energy profile. The potential energy profile is a graph that shows the energy increasing on the vertical axis and time increasing along the horizontal. Now the potential energy profile starts out with the reactants at some arbitrary energy along the vertical axis. And then as the reaction progresses, what you'll notice is that as the reaction progresses, you'll notice a little bump in energy before the energy cascades down to the end, which is where the products are located. Now in the past we've drawn these potential energy profiles that just kind of look like this, where they just kind of fall off a cliff and go down to products. But now we're introducing the idea of a little bump in the energy, and that right there represents the activated complex. This is the energy required to get the H2 and Cl2 to form that little HCl square looking molecule. This is the point where the activated complex is formed. Now at that point, once that's formed, then these bonds of H and Cl snap. The bonds of H and Cl are formed fully, and the reaction proceeds to the end, down the hill to the products, HCl and 2 molecules of it. Now this energy that I've drawn in red is what is known as the activation energy. Sometimes referred to as EA, subscript A. Now, all chemical reactions have their unique potential energy profile, and some of them are exothermic like this one, and some of them are endothermic. This one's exothermic because the products end lower than the reactants started at, and so the overall energy is negative. Now, I'm going to show you an example of an endothermic potential energy profile of a very common reaction that you're familiar with. The reaction that I'm going to show you is that of decomposition of water. So I'm going to draw the vertical axis. Once again, this is energy. This is time, just progressing at a random or arbitrary amount. Now the reactants down here is going to be, or are going to be, 2 molecules of H2O. Now we're going to need to put in a ton of energy in order for that reaction to reach its peak. That area up here known as the peak was where the activated complex is formed. Now this whole energy from the reactants all the way to the top is the activation energy. It's the energy needed to make a reaction proceed. I didn't mention that before, but that's the definition. It's the energy required for a reaction to trigger the activated complex and then proceed spontaneously to products. Now this threshold, or this barrier boundary, the bigger it is, the more difficult this reaction is likely to happen at normal ambient temperatures. Now if you have something that has a low activation energy, these reactions happen almost spontaneously without any other outside energy. But this particular reaction is never going to happen at room temperature. No molecule of water is traveling at the right energy needed to form the activated complex. You'll actually need 2 water molecules to collide at the right energy, at the right orientation to form the activated complex. Now, this activated complex, in fact, forms 3 molecules at once in a weird little dance that it's more complex than I care to show you today. But just know that at the peak, the activated complex is formed, and then at that peak, the reaction then goes to completion. The 2 products are 2 H2s and 1 O2. Those are the 3 molecules I was referring to before. But this reaction starts out at this energy and ends at a higher energy, so there must have been an overall energy input, which is, as I mentioned before, an endothermic reaction.